And here, in terms of Bio-Nano things, these are for the health applications. I did also a lot of research on that the last 15 years. Bio-Nano scale machines, but these are for the injecting into the body and always monitoring the health problems. And that is also really going really well, like with these COVID vaccines. It's going that direction. These mRNAs are nothing than small scale, nanoscale machines, right? They're programmed and they're injected. Bio-Nano scale machines, but these are for the injecting into the body and always monitoring the health problems. And that is also really going really well, like with these COVID vaccines. It's going that direction. These mRNAs are nothing than small scale, nanoscale machines, right? They're programmed and they're injected. So thanks a lot for coming to my second talk. And this is my last day. I mean, I hope not of the life, right? I'm leaving for America after almost 7 weeks here. And I have to say, when I was younger, I loved America, so I was always happy to go back. But now it's like, it's not fun anymore because America is really dangerous and I rather prefer to stay here. But anyhow, but they don't like me here, so I have to leave. Right, Jennifer? Yeah, so she keeps saying that. Okay, so I will present you the work that I started almost 2006. And so I will give you a background story. Actually, when I tell these things to you, it will teach you about research approach. Because there are a lot of people in my 43 years career, they just hear something, they jump, and then they say, okay, I'm an AI person now, machine learning and robotics and all that. They keep jumping around, they write 100 papers with 100 different people. That's really bad practice, okay? So how I started this, 2006, I had 4 PhD students, 2 actually, one of them you work with, Northeastern, is now very famous. Actually, all of them are famous now. But so 4 of them, 2 Turks and 2 Italians, were on the market, and they came for professor positions. So they came back, they said, Professor, all universities are looking for nanotechnologies people. So I said, well, because when I was young in 1970s, early 70s, I went through the microchip era. So when I was taking computer architecture class, I remember those times, like the microchips, etc. And then I realized that when these nano devices, nano-based chips are on the market, and nano machines will come out also on the market, they need to communicate someday. So I got curious about nanoscale machines and their communications. So, and I said I will start the program at Georgia Tech when I was there. And in the meantime, those 4 of them found professor positions. Now they're IEEE fellow and very famous people. So I started, and you will see the entire story of the last 15 years. And I had enormous success with that. So when I started this nano research, nanoscale machines, they're not like your nano robot or drones, right? These are very, very small scale machines. And then we realized that these machines, because we designed graphene-based, graphene is a material, graphene-based antennas and transceivers, etc. And we realized that they communicate the best on very high frequency bands, okay, like 100 gigahertz and up. So that's why I ended up in terahertz bands. And we did all this research. So here's the story, right? So why is an old problem revisited? Again, 2014, we wrote 2 papers. You will see them here. Well, it's not going. Hello, Filipinos. It's stuck. We have this problem also in America, so it's like high tech. What did you do? Okay. So you see here the last 2 with my former students. They're also like very successful now in Northeastern and also Shanghai Jiatong University. And that time I wrote a proposal, large proposal. We got rejected 2014. And then everybody said it's too early. And I remember I wrote a proposal to Intel. And the stupid guy said, oh, that's too early, too long out. Intel, can you imagine this? So I'm sharing this experience with you so you will not be disappointed if you have similar experience, right? And in the meantime, the last 3-4 years, just before the COVID, so everybody started to talk about 6G, and terahertz is the core spectrum band for the 6G, right? So now you see hundreds and thousands of papers on terahertz, really. So then I got invitation to Transaction Communications because our papers get high citations to write a new view of the problem. And so I collected my former student, Shuaini, is also in America now, one of my last PhD students at Georgia Tech. So we wrote this paper. So it's a pretty long paper, by the way. So let me give you the 5G to 6G. And everybody, sometimes, it happens that you respect professors. And then when I was young, I used to dig their knowledge. I was always a troublemaker, just to know how much they know. Some of them didn't know any crap, really. So like also when you ask, what is 5G actually? Everybody says, oh, higher data rates. Actually, the 5G, just for the record, what is it called? Like for example, 4G, the MIMOs, right? Massive MIMOs are the important core technologies. For the 5G, the most important technologies are software-defined networking, SDNs, and network function virtualization. Everything is softwareized. Okay, that's really the basic. And then the 6G will be, again, the basic ideas will be, of the core technologies will be very high spectrum bands like terahertz, but also more. You will see, some more technologies that I will show you in the next slide. So when we look at from the peak data rates, from 5G, like 20 gigabit per second, will go like 1,000 plus terabit per second data rates. And peak spectral efficiency from 30 bits per second per hertz will go to 60 bits per second per hertz. And the end-to-end latency is the biggest problem. Still, in the 4G to 5G, for example, we are talking about here, I hope I can show you here. No, here. So it's 1 millisecond. And in the 6G, we are talking about like almost 0 or 0.1 millisecond. To my knowledge, for the 5G end-to-end latency, if you can get 10 milliseconds, you should be happy. Okay? And then reliability should be very high, 10 to the minus 9 compared to 10 to the minus 5, packet error rates. And then the cell edge data rate, right here you can see, is from 0.1 to 1 gigabit per second. However, here's another important issue of 5G as well as 6G. The cell concept is moving out because you have these controllers, right? Everything is softwareized. The controllers are running the software, and the cells, the towers, will be controlled by the controllers. So just this rigid cell concept will be removed. So you can have multiple base stations. It's kind of like virtual cells, like 3 of them are one cell or 5 of them one cell, right? So then this cell edge data rate becomes unimportant in the 6G. And then, of course, mobility 500 to 1,000 plus mobility kilometer per hour. So now this is my interest, in my view, of the technologies that we put in this paper. It was a long paper, or it is a long paper. So what are the key enabling technologies? Okay? So first of all, terahertz band is, as I told you, the core spectrum that will be really moving the technology ahead. And then there's no order, by the way. There are these surfaces. Last time I talked about the underwater surfaces, but they will also be, actually, that started with the terrestrial, right? So the reconfigurable intelligent surfaces will be very important, okay? And then this is a very interesting idea, actually. And I talked to our small group in this lab about reconfigurable front ends, and actually eager to develop this multi-mode hardware from the underwater. But that starts from that, because USA started 5, 6 years ago, so-called JUMP program with DARPA and Semiconductor Research Corporation, saying we should have hardware front ends, that they should be independent of the one spectrum. Like one front end could recognize all the spectrums and then seamlessly lock into any spectrum. So that's really a very interesting idea, but unfortunately, the progress is slow there. And then accordingly, when you have these reconfigurable front end, then you can realize the dynamic spectrum sharing easily, right? Because the entire spectrum will be in front of you, and then you just sense which spectrums are available, boom, you lock in, and then you transmit your traffic, right? So I have also a lot of work and information, but I will not be able to cover it. And then ambient backscatter communication. So that's also, it's very important. It goes to the energy issues, right? So what you do is you transmit and you emit energy, right? So from that emitting energy, you can harvest the energy back to the device so that you can, prolong the life of the equipment. So there is also a lot of work on the market now, ambient backscatter communications. And of course, everybody talks about MI and machine learning and AI techniques. And then here is the network automation that goes with the software-defined networking, network function virtualization. That is slicing of the software that Osama is doing that for the underwater cases. We have also patents in this group here. And this is for the terrestrial I'm talking about. And then self-free massive MIMO communications. That goes exactly with the idea of that controllers will control all the base stations, and the notion of the cell disappeared. So that will be self-free, right? Again, many activities are there. And then you see on top, CubeSats, UAVs. That's also, this lab is very interesting work, doing research on that. And also I call them Internet of Space things. So today I will talk about those 3 green areas. And then I could talk like 4 or 5 hours about all of these, but the paper covers everything in detail. And then there's 3 parts, right? So you see, I put them under 7G. There is a reason for it. So first of all, quantum computing, quantum communication, especially quantum computing, is on the market. I call it the research market, right? So since 1990s, quantum computing, and the progress is extremely slow. Really, it's sad to see. Only in cryptography, in error control issues, they have a lot of progress. And now again, the last 5, 6 years, a lot of money is getting invested. Progress is slow, especially for the quantum communications. I think we need at least 10 to 15, 20 years to have this full-blown, like, for example, a quantum cell phone. Right? That will be fantastic to beat the propagation delay problems in the communications. And then here, in terms of Bio-Nano things, these are for the health applications. I did also a lot of research on that the last 15 years. Bio-Nano scale machines, but these are for the, injecting into the body and always monitoring the health problems. And that is also really going really well, like with these COVID vaccines, it's going that direction. These mRNAs are nothing than small scale, nanoscale machines, right? They're programmed and they're injected. And then Internet of nanoscale things. So those will be part of 7G and beyond, right? So let's talk about terahertz band. Why terahertz, right? So I just showed you the 6G requirements are very strict, like very minimum end-to-end latency, like 0.1 millisecond. Even they are saying we should go like 0 milliseconds, right? And then very high reliability and very high data rates. Okay. So now, for example, when I gave talk about the metaverse here last October, like these holograms and also the extended reality, they need really very, very high data rates. I showed you like terabit per second, and also latencies are extremely small, right, low. And then the wireless data traffic is exponentially growing. And there are more and more devices, like by 2020, we have like 12 billion devices, mobile devices. And then also the wireless data rates are being doubled every 18 months over the last 3 decades. So that means we need wireless terabit per second links. And but how can we realize that, right? With the lower frequencies, we cannot realize these. So even with massive MIMO or ultra-massive MIMO. So we have to really explore these virgin frequency bands and realize these terahertz. So this is the, again, like old slide here when I was trying to convince the sponsors, like this is no man's land that time, Now it's like many, many people in the world are working on the terahertz band. So, millimeter waves, I never worked on the millimeter waves. I work a little bit because the payoff is very little. You work on, for example, on millimeter wave bands in 60 gigahertz, and the useful spectrum band is like 7 gigahertz. So the payoff is not that much. So why do you do all this research? So that's why I put here the advantage of terahertz versus millimeter waves and optics. Higher data rates, like terabit per second, can be easily realized. Higher directionality and smaller footprint. And they're less susceptible to free space diffraction and inter-antenna interference, and higher resilience to eavesdropping. Okay? And they are less affected by ambient light, atmospheric turbulence, scintillation, cloud dust, less delicate pointing, acquisition, and tracking, and can exploit reflection and array processing. So these are the advantages. So I told you, in the meantime, I started many, many projects in the US, like NSF and Army were the major sponsors, but also I got to finish distinguished professor project in Finland for 5 years with Tampere University, and I created a center in Catalonia and Barcelona, Nano Networking Center, and I'm sorry about the promotion here, or commercial. Then I got Humboldt Award, the first 14, 16, and now I have another second one, so I'm going there for mobile terahertz band case. 3 months I'll be there, Humboldt Award. And then I even started in Saudi Arabia Research Center in Jeddah, TAX, that's their National Science Foundation in Riyadh. They paid that amount, and then many, many other cases. So in the meantime, like, I don't know, maybe 60 people worked on these topics. And so what did we do? This is a big picture here. So first of all, I remember I told you these devices, the nano devices were being developed, and mostly for computing purposes. Then I realized that for communication, we needed transceivers and antennas. And then we did those, I will show it to you. And then we used materials like graphene, and then we realized that they're working the best in terahertz band. And then we checked, there are all these textbooks, right, and papers on gigahertz and megahertz and like channel models, etc., right? And then terahertz was really virgin territory at that time. So we did all this classical research like propagation modeling and then noise, capacity, all of that here. And then we also realized that these 5-layer solutions, all the modulation, synchronization, holding, whatever you think of. The ones that we are using, they cannot be used. They are too heavyweight. So we realized developed some new bilayer solutions. So I will share with some of them with you. And then, of course, for the networking part, so when you put these devices together, all of these issues were open, like, MAC protocols, addressing, routing, relaying, etc. Right? So, and then what we did is we finished many of these, and we used ComSol simulation tool to validate most of these solutions. And then we're supposed to fabricate. Fabrication is the most difficult part. And Josep is trying you will see that. And he just keeps writing papers, unfortunately. But anyhow, so we'll see that. So the first one was the antenna case. Okay, the first paper was published in it was in Europe, antenna conference, 2010. And then we got a patent in 2017. This patent took long, so CIA put a lock on it without releasing it. They were sitting on it a long time, and then they finally released the patent. So then we have also journal publication. So as you see here, that graphene always works on top of a dielectric material, like gallium nitride, gallium arsenide, like this thing here, right? Dielectric material, and then this grid type, that's the graphene. If you never heard of graphene, it's really very interesting material, by the way. And let me give you an example. It has like really fantastic characteristics, right? Harder than steel, and then it can take care of the EM waves much faster than any other materials. And the inventors are Gaim and Novoselov. And I used to tell people, I remember I gave a keynote exactly on this topic in PMRC, which is a famous IEEE conference, and September 2010. I mentioned that Gaim and Novoselov will receive the Nobel Prize in 2017 and later on. This was 10, right? And then 1 month later, they announced that they received the Nobel Prize. They're the inventors of the graphene. And they are professors at University of Manchester. They are originally from Turkey. No, they're originally from St. Petersburg. And but they left, and Putin gave them a medal, but they didn't accept it. But anyhow, this is political things. And they are the first who demonstrated 1 nanometer conductor, 1 nanometer transistor in the history. So that was back in 2008. So what we did is we put this graphene, so electromagnetic waves are hitting this surface, right? As you see here, they propagate the best efficient radiation using these so-called surface plasma polarity waves, SPP waves. And then we realized that these SPP waves perform the best in the higher frequency band, 100 gigahertz and up to 10 terahertz band. So the in between, they're like graphene and also dielectric material. So the global oscillations of the electrical charge at the interface between graphene and dielectric material realize this communication, okay? So then we also needed a transceiver, right? And so as you see here, we applied this 2 years later, but then we got the patent earlier, 2016. So I just give you a basic idea here, right? So again, dielectric material, the graphene here. And so you can see the source gate and drain. So this idea of the patent is based on the so-called HEMT, high electron mobility transistor. So if the voltage at the drain is higher than voltage at the source, and then when a sufficient large voltage applied to the gate, the transistor becomes on, and electrons can move from the source to drain. And there's no voltage at the gate applied, the transistor is off, and electrons cannot move. So that was a simple idea about HEMT technology. At the receiver side, so what we do here is we needed a very fast signal detector because the signals are coming extremely fast, and then the ones that they were on the market couldn't be used. So we developed also a signal detecting technology. And then, of course, you will see later on about all these other issues like synchronization, et cetera, right? So that's the receiver side. And then the front end looks like this. I mean, it looks huge, right? That's not that much, like 10 millimeter. That was our design idea. So it looks huge, but it's not. So that's the front end, the antenna here, and transistor there, okay? And so this was the full-blown front end we developed. And the next question was, based on the ComSol simulations, that they perform well at the terahertz band. And we said, how does the terahertz band behave, right? So now, again, there's a lot of mathematics here. I skipped that. I'm not teaching you high school math here. So what happens is the following. So the basic idea that we also validated through ComSol simulations, as well as we had some test bed, which we're working on 350 gigahertz in the lab. So what is interesting that we observed is the terahertz band communication is extremely distance limited. So when you look at the indoor, for example, when you have more than 1 meter distance between transmitter and receiver, the path loss is so bad here, as you see here, the totally red, so you cannot have a meaningful communication. So when you have below 1 meter, as you see here, right? So now you can have some sub windows here, like the yellow areas. But you can have meaningful communication in this range below 1 meter. If you go beyond 1 meter, then there's a problem, as you see here. So that was the observation, mathematically, as well as COMSOL, as well as through measurements, right? And then now, in the last 3-4 years, they keep writing papers on this, which is old now in the meantime. So now we realized this was like back in 2010, right? So then I devoted almost 10 years with all my people that you will see names. How do we combat the distance problem? Because otherwise nobody will use it. So so now I will come back to these issues about distance, right? So now next question was about the physical layer problems, right? So we developed this new modulation technique, which was called T-SUC, time spread on and off keying mechanism, which is a very simple idea based on femtosecond long pulses spread in time. So what happens is when you have a 1, you have a very short femtosecond long pulse, and you have some time interval here, another femtosecond long pulse, and then we we got a project also with my other colleagues at Georgia Tech. They, some of you may know Jeffrey Lee, Marianne Ingram, and etc. So they did all the optimization, which will be this time interval TS and optimum, and also the pulse length. We used 100 femtosecond, but then they also developed some optimization techniques. How long should be the optimum values? The pulse energy used for each femtosecond long pulse was less than 1 picojoule, and 0 was coded as silence, right? So when there was a 0, there was nothing. So just silence. That means we needed a perfect synchronization between transmitter and receiver. When there is a silence, the receiver will code it as a 0. So it was not easy, right? And they could easily get out of sync. So that's why another hurdle for the distance problem. And then, so this also helps us for the MAC protocols, right? So because when you use these, let's say like the 2 transmitters, very short, long, femtosecond long pulses, the probability that you will have collision is almost going to 0. It's not 0, but it's almost going 0. And then 0 is mostly silence. That means the MAC protocols can easily be designed using this idea of femtosecond long pulses modulation technique. Okay. So now we also showed that in the time domain, as you see here, in the amplitude 2 terahertz band. I'm sorry, 2. This is the time, 4,000 femtosecond, and 2 gigahertz. I'm sorry, 2 terahertz, right? Is the maximum. And then here in the frequency domain, as you see here, like 2 gigahertz, terahertz. Why am I always gigahertz? So in the frequency band. So the time as well as in amplitude and power spectral density are shown here based on our measurements as well as on our COMSOL simulations. So why femtosecond long Gaussian pulses? I explained to you that actually this technology is used for nanoscale sensing and imaging. For example, when you are at the airports, you move to a cabin, right? They're using those femtosecond long pulses, but that's not for communication, just for sensing and imaging, okay? And then also these pulses are 3 orders of magnitude shorter than the infrared ultra-wideband systems. Accordingly, you can have less collision probabilities, as you can see. Plus, less energy usage because the zeros are not transmitted at all, just silence. So now, the grand challenge, as I told you 10 years ago, I realized it's a distance problem. And how can we combat this, number one? Number two, especially after 10 years or 8 years, I got tired of the indoor, right? So I wanted to go outdoor mobile. And then I contacted the U.S. Army, and they were very interested because of the military applications. And I also did a lot of work on the outdoor and mobile terror systems, but the research problems are still open, many of them. Right? It's a very long way to go. So this is the paper that we wrote in June 2018 with my 2 PhD students. They're again professors. And I was about to tell it before the talk. I graduated again, promotional second. So I graduated 50 PhD students, and I pushed them always to become professors. And maybe 30 of them are professors worldwide. And then I realized many of my professor friends, they didn't care about their PhD students. And then I look back, of course, I'm extremely proud that they are famous, but then there's a reality. Now I understand these bastards, why they didn't do it. Because you create competitors to yourself. Some people, of course, continue to be part of them. I don't like that. I don't like to be tail of my former people. And, but then, they compete with you. So, but again, it doesn't matter because I continued my life. So I'm really proud of all those achievements of my people. Anyhow, like, for example, how do we extend the communication distance, right? So we looked at multipath effects because multipath effects, when you know digital signal processing, so it can have negative and positive effects. When you have positive effects, you can go longer distances, right? And then you have seen these sub bands. We said, can we look at these sub bands, those sub windows, and use distance adaptive modulation technique? These were all vitamins, right? You didn't solve the problem. And then we said, can we come up with something, everybody talks about MIMO, right? So we developed a new patent and also contribution. We call this ultramassive MIMO, very large number of antennas. I will show it to you. That really helped also. But again, it didn't solve the problem totally. And then, remember last or 2 weeks ago, I talked about surfaces. That's why I ended up there. And you see how everything goes, binding together, right? Because I gave a talk about these things in 2011 in Cyprus, and we started to talk about these, distance problems, etc. And surfaces. Now everybody is outside talking about surfaces, which helps us, right, to get citations. So this first multipath effects we published in Transaction Wireless Communications with these two former PhD students. And another thing that I don't practice in my entire life is I only work with people that I work really, like either my PhD students, my postdocs, my visitors, or like here I'm involved. I got maybe thousands of the last 40 years requests. Can we put your name on our papers? I always said no. And I was even upset about that. And then, people know that they cannot approach me with that crap. This is fun, right? You do research there. It's not like Oriental Bazaar, put me there, put me here. You must, each paper I know the stories, I can tell you, because it's all blood, sweat, and tears, It's not like you put it there, I don't care. Well, so anyhow, so this paper, we want to expand the distance, right? So you can read that, but what we realized is when we use the multipath effects, it can really increase the distance a couple meters. I showed you 1 meter, but we can go a couple meters, but it didn't help too much, So this is like the multipath effects. Then we looked at the distance adaptive modulation. Remember, I have these sub-windows, right? We said, okay, we'll look at the channel behavior and say, can we find sub-window? And we try to transmit in the sub-window, right? And then, of course, we needed spectrum allocation principles and also some new ideas. And then we realized again, two things. One is when you use sub-windows, you do not have too much spectrum, right? So always sub-windows. Of course, you can composite them, but that doesn't help us, right? We don't fully utilize the full spectrum. So then the second thing was it was also slowing down the transmission and receptions. So this didn't help us either, but we published transaction signal processing. And now another idea was, again, a long time ago, we created this ultramassive MIMO. As you see here, these are the graphenes and sitting on top of the electric material. It's like 1 to 10 millimeter surface. And there's a plasmonic nano antenna here. These are the wavelengths divided by, surface plasma polarity waves divided by 2. That means a normal wavelengths should have long distances in massive MIMOs, right? So that you avoid interferences. With these lambda SPPs, we can have shorter distances. The interference will not be a problem. So we got these 32 by 32, meaning 1024 elements available to us. So, and then, all these very interesting results through the simulations, COMSOL, as well as, it's unfortunately not fabricated yet. It's really not easy to fabricate these things, really. And since 2015, we are waiting, but it's very, long way to go. So we realized through COMSOL simulations, ultramassive MIMO can at least 10-fold increase in transmission distance at 300 gigahertz and 1 terahertz compared to massive MIMOs. So that was a good contribution, in my opinion. And then there are other beauties of this invention. Is we call this dynamic ultramassive MIMO for intelligent beamforming. So you see here all these arrays, right? We have these different sub-arrays, and then we can create dynamically these different beamforms, okay? Or they all can together collaboratively work together, and then you can have razor sharp or pencil sharp, some people call it, and single focus beam. And then when you use this, for example, you go very, very long distances. Plus, we can apply machine learning algorithms to do intelligent beamforming. Chinese, we published in ICAS 2020, and then she's still continuing that at the University of Nebraska. And same way here for the, like these multi-band ultramassive MIMO. So normally you have all these homogeneous spectrums, right? You can also have multi-band, different spectrum bands, and they can be packed in these arrays, sub-arrays or the entire array, and you can realize these multi-band ultramassive MIMO here. We also did some, in 2021, do I have it here somewhere? Yeah, here, codebook design, which I need, but still there's a lot of work to do for this part. And then of course, fabrication is still open question. It would be good to have some group here to do that, but anyhow. So these are the, we did some, channel modeling, etc., publishing some of these conference and journals. So now, that research is continuing in the world, but also I said I was interested in 17, 18 about outdoor cases because the challenges are much more. So first of all, longer transmission distances. By the way, I have to show you back there a little bit. So because I skipped many of these details of these things here, right? Like for example, in Germany, we call it Mr. Equalizer in Erlangen. we did that work. Same thing with synchronization in my first Alexander von Humboldt. And then we have some MAC and error control. And then all these papers are published in many, many conferences and journals. So, okay. So now let's go to outdoor, okay? So we have longer transmission distances. There are high attenuations. And then shadowing effects caused by dense obstructions, such as buildings and all these other obstructions, as you can imagine. Higher signal energy dispersion caused by frequency selective fading. Then higher mobility of transmitters and scatters in environments, which lead to larger Doppler shift and scintillation effects, especially for the like drones and also for the CubeSats and satellite technologies. Okay? So there are many, I mean, this is like a laundry list. People are really writing so many papers, but they don't touch these things. For example, how do you acquire the CSI in rapid time varying terahertz channels? Okay? And then how do you detect, localize multiple mobile users and objects in these, especially when you have ultramassive MIMO, hundreds and thousands of the channels, right? And then what about resource allocations, like joint spatial temporal correlations and spectral domains as an optimization problem? Okay? So like if you want to use for the high-speed vehicles and random trajectories, how do we realize real-time beam tracking schemes? So here's a summary of these challenges, right? Like especially outdoors, 3D end-to-end channel characterization, polarization, diversity, mobility, realistic terrain environments. Can we use machine learning for all these optimization problems? And then environmental adaptive solution for modulation coding schemes. Transmission distance analysis, especially when we are outside, right? I told you about the indoor, but outdoor it will be much more challenging. And then also cross-layer protocol design. And then when we use ultramassive MIMO, like indoor, we did these mutual coupling effects, and it will be interesting to look at, how will the mutual coupling effect will perform in outdoors. All spectrum access, right? Like these reconfigurable spectrums, right? And all these other, modulation coding schemes are open issues, right? And then here are the more questions about synchronization. The terahertz clocks are unreliable, phase noise and clock skew problems. And can we use, some like atomic clocks, for example? What type of MAC protocols can we use? Okay, so these are all question marks. And then the routing problems are open, especially outdoor. We have ad hoc, right, multi-hub networks. And of course, computer science people always develop these routing algorithms without looking at the physical layer effects. Normally they say SNR, signal to noise ratio, but normally, you must look more like, terahertz effects and all the physical layer effects, and then accordingly develop your routing metrics and decide about it. And then, of course, end-to-end reliability are also open. And error control is really interesting. What type of ARRC or hybrid ARRC, error prevention codes. We use low weight codes. Do I have it here? I don't have it. But it was published like almost many years ago. And low weight codes. It's more like estimating there will be error and then try to avoid. It's kind of like Wi-Fi 8.11 CSMA CA, right? Collision avoidance. So we try to error avoidance solution, right? And so, but again, they were just ideas, right? So here is the terahertz band is still not regulated, by the way, okay? So there is a group led by Braunschweig in Germany, Thomas Kerner. They had like last week or Monday, another group meeting. I don't go there anymore because it's all BS, right? They're whirling around and around. So I don't like these standardization group meetings. They're looking at 100 gigabit per second. And it was established 2014. And then in 2012, they established these 3G, what was it called? IG terahertz, right? Interest group terahertz. And they looked at 300 euros to 3 terahertz. And I was heavily involved in those. But then this became like a really, typical standardization. And you just meet and BS around and go home. But if you are interested, I can share the websites. It's really sad. But anyhow, so here's another thing that I want to show you. So the DARPA is the Defense Advanced Research Project Agency. They introduced the internet, as you know, like in the 60s, 70s. And they published an article, 2014, 4 DARPA projects bigger than the internet. So there are these 4 cases, right, in 2014. Atomic GPS, right? And then a virus shield for Internet of Things, rapid threat assessment. Here, voila, terahertz frequency electronics, devices, metamaterials, and communication. You see? We were right at that time. We started like 06, 07. Another promotional second. No, but really, it was coincidence. Anyhow, so I think I will skip the reconfiguring intelligent surfaces because you know that from last talk. So I will go immediately to the last portion. This was our patent. It's a really neat idea, really. And this was supported by FET, European community. That's the prototype. Maybe I didn't have that picture last time. This was a prototype by the Fraunhofer Institute in Berlin. And this was the group of people, right? You remember this? We had like 40 people, but some of them are not here. They were in the bathroom and all that. So lunch break. And so like here, I did not show you this. Maybe some of you do vehicular technology. These surfaces can help you also like combat these non-line of sight problems in vehicular technology. And also like tracking will be easy, right? Like for example, location 1 and it moves here, and then you can track them with these surfaces, right? It's really interesting, real-time beam tracking scheme. I cannot pinpoint because really it's not easy to follow all papers. There was a cartoon, a friend of mine sent it to me, maybe you know that. You don't need bathroom tissues anymore, go to archive or whatever, right? So everybody writes papers and puts on the archive, right? So there really, it's not easy. So I'm happy when I look back when I was young, it was easier to follow the research, right? Now it's like every day hundreds of papers are uploaded and everybody does something. I feel sorry for some of you, but I have to tell you, 80% of those papers are junk, I can tell you, really. So some people say, oh, I have transaction paper. Who cares, really? It's the quality is important. So here is the problems of the surfaces. There is no standards, really. And I think we need a standardization. Maybe somebody created it, I don't know. But and then also, this is a common problem. Many of you do practical research. The companies are always exaggerate. Yesterday we were talking about some cases of the drones. So like I remember 1995, I was in NASA working there for summer. And then we had these ATM switches those years. It's supposed to be like 40 megabits per second those years, right? We couldn't get 4 megabits per second. And then the guy was cursing right and left loud, and they cheated us and all that stuff. So they say, oh, well, next version will take care of it. So in other words, for example, when I read the news or LinkedIn, like ZTE, I have a friend there, Richie Lou. Oh, we have some demo, everything is working. That's not true. It's like the market is not ready for the surfaces, okay? So don't say I go to company X, I buy it, and it works. And like Meron's people have a surface here. They bought it from a French company. They have severe problems. They were telling me about this. So in other words, we need standardization and also be honest, to hit the market, right? So, with some good products. And so this is still open. And also, how will these surfaces work in 5G and 6G with all these heterogeneous networks, right? Because we have all these networks that we're using. So how will they perform, right? And then the other thing, my criticism that I mentioned in the on the water case time, that many people, especially comm theory people, they treat this like as a box. Signal comes in, goes out, I do all the mathematics. But what do you do, What do you bring to the market? Nothing. Just nice formulas. So now I have another cartoon. So this guy has like entire blackboard full of equations. And then his friend puts there 2 + 2 is 4. And he also has 4. So why? I mean, you do all these things, but then what do we do out of it? Actually, the real game is here in the inside. So you have to understand how the surface works, improve or make it available for the market, right? So that's my criticism to the community. Like our group really wrote, go to the wisersurf.eu, maybe it's here. That's like, I think this is really a good model for a lot of research, but we had so many people like, antenna people, physics people, material people, communication people, everything, right? So like, it was a very good team, really. I enjoyed working with them, wisersurf.eu. So we did really good stuff, in my opinion, but my baby is more beautiful than your baby, right? So anyhow, so we can also use to combat the distance problem of the terahertz through these surfaces. Oh, what we did is the following. I have to share with you. So these surfaces, when we use the metamaterials, they work very well for the lower spectrums. For higher spectrums, we use graphenes. Please keep that in mind. And when you use metamaterials for the higher surfaces, they not perform well. So you have to use graphene to get the best performance, right? And so let me talk about this here. Maybe it is more interesting to some of you because you do drone technology. So this is a concept called small satellites, right? So I was interested in CubeSats. How did I get into the CubeSats? Let me explain you that to this story. Remember, blood and sweat and tears, everything. So in the 90s, I did a lot of work for NASA, really. But LEOs and GEOs and we have so many papers and really interesting work those years. And in 2004, NASA had the accident, they burned when they were coming in. And so the NASA had problems those years. The money was gone. I was gone. If there's no money, you cannot do research, right? And then 2016, I was in University of New Mexico giving a talk. It's in Albuquerque, New Mexico. And then there's an Air Force research lab there. They brought me there and they showed me these CubeSats. I heard about CubeSats before, but then I was really impressed how advanced they became, right? So they were really fantastic. And then I said, I will do research. But the question was, how can I get into the research, right? So another thing that I share with you is when you find some new research, don't say I'll write N+1 paper, right? So you have to find where can I get, which angle can I come in, right? So that it will be new. So that's why I start the research. I will show you these things. So now I learned all these things later on. Like there are so-called mini satellites, microsatellites, like the weights are different, right? Nanosatellites, like CubeSats, and 1 to 10 kilogram, picosatellites, and femtosatellites. So that's the umbrella is small satellites, okay? So now we can create these Internet of Space things, right? Like CubeSats, LEOs, and GEOs all over the place, right? So remember I told you that I needed some new angle. And so I will show you this new angle to you, what we discovered, and then write a couple papers and also a patent application. And then we got in October 22 this final patent now. These were my last PhD students. Jennifer knows them. And so what are the applications? Many, backhaul in the sky, like, pervasive tracking, remote areas connectivity, energy infrastructure after natural disasters, network security concern in terrestrial networks, traffic offloading from congested terrestrial networks, eyes in the sky, you can monitor the terrains, or also disaster prevention and monitoring. So there are many, many applications that you know also from the drones, right? So what is CubeSat? So let's talk about that. So the idea was, I have a new, actually I finally put the name of the guy, but now it's another talk. So there's a old NASA guy. Normally, when you look at all this research, it's done in the top 10 universities, and majority of them in top 10. So this guy is working California State University, which is a teaching school, but he came up with this, but he had NASA background, right? I forgot his name. I updated, but now I cannot find that slide. So here's the thing. The unit is by U. So if it's 1 unit, it's 10 by 10 by 10 centimeters. It's like a Mach size, right? It's called CubeSat. If it's 3U, 30 by 30 by 30 centimeters, or 5, 50, 50, 50, 12, 1.20, etc. So that's the way these CubeSats work, right? So, and then I realized, remember, after seeing that for the military, but there are also many civilian applications, right? So now, for example, some of them I cannot go through all of them, like, Switzerland, Australia, Canada, Spain, USA, and UK, they have all these different CubeSats. And like they have different orbital altitudes, like 500 to 600 kilometers, okay? 800 up to, even what is this guy's name? Elon Musk has his Rin Tin Tin. Is it here? It's not here, but anyhow, I have another slide. So then the number of satellites, 6,400, etc., and then their weights, and then also the operating frequencies, and then their sizes, right? 6U, 3U, 1U, 12U, etc. So these are all for civilian applications. And so when I, not only military, but also these civilian cases, and then we found all these angles, okay? First of all, you have seen all the numbers, right? Number of satellites. And these numbers are not enough to cover the entire Earth at the same time. So there's no global coverage, right? Continuous global coverage. And then also we realized the data rates are low, like in acoustic case, right? They're not using acoustic, but anyhow, like kilobit per second, 1 megabit per second, etc. Like you can go at most to Kepler like 1 to 40 megabit per second, but still with the old 5G, 6G requirements, they are still low, right? And then no publicly available solutions for large-scale network constellation design. And then also they are still using onboard processing. Onboard processing meaning is exactly anti-softwareization, right? So the satellites have processing capabilities. So all the software is running on the satellites, and that makes them bind it to certain technologies, right? So when you have updates, it's very difficult to update them. So it's better, we said we can go with 5G, SDN, and NFV cases. We'll put controllers on the ground, and these CubeSats will be dumb devices, right? They will be controlled by the controllers. And then many use cases with different requirements, service requirements. And then data routing is a problem, right? And then we also realized, you will see that the bands they are using are L bands, X bands, Ka bands, Ku bands, like millimeter waves and terahertz bands were underexplored. So these are the angles we found. Okay, so I said, let's start the research, right? So like here, you can see some of the examples that are using these typical bands for the satellite communication. So first, our design is the following. We publish papers and also we apply patent that I showed you. So our case is 3U, 10 by 10 by 34 centimeters, right? Because with the 34, because you have these solar panels, you flap them open and then it becomes like this huge. Normally it's open, it's like become 10 by 10 by 10, right? It's 5 kilogram maximum, no propulsion system, etc. And what are the interesting ideas, right? Again, you have to always, please, when you come up with some solutions, always think what's the novelty, what I do here, right? Because if you just redo another CubeSats, then what is the value of it, right? And you cannot say I get 10% better performance, who cares? So first of all, the first idea was that these inter-satellite links, right? If we use terahertz band communication, there are no atmospheric effects. Oh, I forgot to tell you. So why are the terahertz band distance limited? I totally forgot that, and nobody asked me. So remember, beyond 1 meter, it's red, right? Path losses are high. The reason is when you are in very high spectrums, there are water particles in the air, and they affect signal propagation. Like, for example, in 60 gigahertz, like millimeter wave bands, the oxygen particles are the enemy. For the terahertz band, the water particles are the enemy. However, in the atmosphere, there are no these gas effects, right? So we said, okay, why don't we use terahertz band communication for the intersatellite links, right? And then, but then the next question was up and down, right? We have atmospheric effects and all these scintillation effects, etc. I showed you. And we cannot use terahertz because the performance will be awful. So then we said, okay, why don't we have a reconfigurable front end idea, right? Like multi-mode, but more for different spectrums. And then, like from 1 gigahertz to up to 2 terahertz, for example. And then these devices will be able to have these reconfigured front ends. That means dynamic spectrum frequency access. And then third idea was that we will use controllers like SDN and FE, that the controllers will run on the Earth segment or ground segment, and they will control everything from these controllers. Like our work with Osama for underwater, right? So we do the same thing here. And then slicing and everything is done here in the controllers. And also all the protocols are running on that. So here's the things that I explained to you. We call this multi-frequency band communication. So here are the inter-satellite links using terahertz, right here. Either, I focus more on terahertz here, but you can also use millimeter wave bands. And we did some work on this channel modeling analysis, published 2 years ago. And then for the ground to satellite links, we say we have all these bands available, right? They're already using the commercial systems. Well, we'll add these two, but then we'll have these seamless switch over between spectrums, right? Like in Igor's work, right? We have all these 3 different or 4 different modes. We are saying switch over without time delays, right? That's the catch. And here's the same way. So we should be able to, sense the spectrum and then decide which spectrum we will send up or down, because they also have same here. But internally, they will communicate through the terahertz links, right? So those were the good ideas. And then also we have many details here about this SDN and FE architectures. And so all of them are under that patent described, okay? So now I bored you a lot now because I have 70 slides. So anyhow, so what I want to show you is 6G is really important. The basic component core technology will be based on the terahertz, very high spectrum bands to satisfy these requirements of the 6G. But also there's other technologies like the small satellites, including drones, CubeSats, and also dynamic spectrum access surfaces. They're all important within the 6G. And I hope some of you, I don't know how much time you will have extra to look into these, or you can convert your work to these directions. And I thank you for listening. If you have questions, I'll be glad to answer.